Okay, so now we can go back to the immunization strategy we saw back here in section 3.4 and address some of the limitations that this technique had. So recall we did this technique, it worked, but it only worked under these very restrictive assumptions. Namely, interest rates could only shift in this infinitesimal parallel way. And then the term structure would happen, the shift would happen right now after setting up the portfolio, and then there would be no more changes in interest rates. Okay, so let's first address this restriction that it has to be an infinitesimal shift. Okay, so now we have convexity, and we are going to use this idea of convexity to improve the immunization strategy. So we are going to be able to build an immunizing portfolio even with discrete, not meaning they don't have to be very small, very tiny. They can actually be what really happens in reality, which is large changes in interest rates. Okay, we are still assuming that the change is a parallel change, like we have done so far. Okay, so under this more general case of discrete parallel changes, the immunization rule is this one that you have here. The first two are exactly the same as we had before, namely we have to fully fund the liabilities, meaning the present value of the assets has to equal present value of the liabilities. Second, we still have to match the durations. So we have to build a portfolio of assets that has exactly the same duration as what we are trying to immunize, the liabilities that we're trying to immunize. But then the new condition, the additional condition is number 3. Okay, so we are also going to force the assets to have a convexity that is larger than the convexity of the liabilities. Right? So if we do that, if the portfolio of assets satisfies these 3 conditions, we are guaranteed to have enough money to discharge the liabilities in the future, even if rates change by a significant amount. Okay. Well, intuitively, what's going on is the following. So what I'm going to plot here is the value of the assets and the liabilities at time 0 immediately after the change in interest rates. So this is, I have the portfolio, interest rates change in 1 second, and then let's see what happens. Let me open the figure here and switch to the figure. Okay. So what we are assuming is that we have built a portfolio of assets that have more convexity than the liabilities. Okay, the convexity, if you recall the definition, is essentially the second derivative of the price with respect to interest rates. So basically, the convexity is measuring the curvature of the price function, and hence the name convexity, right? So it looks like this. It's a convex function, but the assets have more convexity, so the curve is tighter, it's close, it's more close. Okay, so what happens? So suppose this is the initial interest rate. We have fully funded the liabilities, meaning that before interest rates change, the values are exactly the same. And now let's think of an interest rate change. It can either be a positive change or a negative change. For example, if it is a negative change, what happens? Interest rates jump from here to here. And what happens is that the value of the assets becomes larger than the value of the liabilities, okay, because of this convexity difference. And then if interest rates do not change anymore in the future, this difference will grow in the future, and by the discharge date, we will have still a positive difference between the assets and the liabilities. All right, so let's do an example. Let's go back to that initial example we had for the immunization in the first case where we were not using convexity yet, so example 341. And let's just understand why it worked. Because For any exercise that we do here, the change in rate, it's always going to be a discrete change. That concept of infinitesimal change is just an abstract mathematical concept. Whenever I put the number there, it is always a discrete amount, right? So let's see why did the immunization really work in that case. Okay, so let's compare the convexities. Let's compare the convexities of the liabilities and the assets. So let me switch to the image. Okay, so again, we had a liability of 1 million in 2 years, and then we had two possible assets: a zero coupon bond with 1 year to maturity, and this coupon bearing bond with 3 years to maturity, and these coupons. In that previous example, we defined these weights such that the durations of the assets and the liabilities were the same. So now let's check that with these weights, we also get that third condition on the convexities satisfied, namely the convexity of the assets larger than the convexity of the liabilities. So let's check that that happens. So the convexity of the liability is the zero coupon bond. The convexity is just the time squared, 4. The assets, we have one first asset, which is the zero coupon bond. The convexity is 1 squared, that's 1. The second is the coupon bearing bond. What is the convexity of this? This is a portfolio of zero coupon bonds, 1, 2, 3. So it's the convexity of the bond is the weighted average of the convexities of the zero coupon bonds. What are the weights? The natural weights, meaning the value of each coupon over the value of the total package of the bond. Okay, and then for each of the zero coupon bonds, I have here the convexity of that zero coupon bond. So 1 squared, 2 squared, it's not shown here, and then 3 squared. Okay, so doing these calculations, I get the convexity of this bond. Since I have already defined the weights, let's check what is the convexity of the assets with those weights. So if I now plug in the weights that we got from the previous example back in the other section, and these new convexities, I get a convexity for the assets of 498. So indeed, the convexity of the assets is larger than the convexity of the liability. So 498 is larger than 4. And that is why this example worked in that first section where we did not talk about convexity yet. But indeed, the convexity is larger, and the convexity of the assets is larger than the liabilities. And that's why it works for that's why it worked for that change in interest rates, and it would also work for any other change in interest rates. So you can try this at home. I'm not going to do this here, but if you now make an even larger change in interest rates, so suppose interest rates increase by full 3%. Recall in that previous example we did in the other section, it was just a small change of a few basis points. Now it's a huge change of 3%. Okay, interest rates were at 5%, and they jumped to 8%. Okay, still immunization works. Okay, again, this would work for any change in interest rates, as long as it is a parallel change as we are discussing and happens right now. Okay. So double check these numbers. The calculations you have to do here are exactly the same as we did in the example in the previous section on immunization. Okay. Okay. The other assumptions or the other constraints on the model were, in addition to the small change in interest rates that is we have taken care of. Now it does not need to be infinitesimal, it can be something discrete. But then we were also assuming that interest rates would not change anymore. There was just one single change that would happen right now, and then after that they would remain constant. And again, by constant I mean they will evolve according to forward rates, right? So let's take care of this restriction. Well, the solution here is kind of obvious, right? So if in practice what I need to do is I need to rebalance the portfolio several times. Okay, so as we go through time, I will every month or every week, or depending on the volatility of interest rates, But at a given frequency, I will need to look at my portfolio and readjust the assets such that they again match the conditions, okay? And then if interest rates change, I am fine. Then I rebalance. And then when they change again, I rebalance, and I keep doing this. Obviously, I cannot do this. I cannot be rebalancing every second, because if I was doing that, I would have so much transaction costs that I would lose a lot of money. So there is a trade-off between rebalancing too often and the transaction costs that that I have to pay to do that. Right? Okay, so one possible procedure to do immunization, given that there is transaction costs, is to rebalance the portfolio, but to try to trade as little as possible. Okay, so what you have here is a program where you are going to rebalance the portfolio, but trying to trade as little as possible. So what we are trying to optimize, the objective function here, is the difference between n bar is the existing notional of the bond I that I already have in the portfolio, and this ni without the bar is the choice variable. So it's the new quantity of the bond that I am going to choose. So basically, I'm going to change my holdings, but just by enough to satisfy the constraints, right? And these constraints are those constraints that we have seen before, namely that the duration of the assets matches the duration of the liabilities, and the convexity of the assets is higher than the liabilities. Okay, so if my portfolio is out of balance, if you will, I will rebalance by just as much as necessary to again satisfy the constraints, right? So this is almost done. I discuss here some alternatives to take care of the last constraint, which was that we were assuming just parallel shifts in the curve. Okay, I'm not going to go through this here in the video because this is just stuff that you can read. The bottom line anyway is that even though we have these more complicated alternatives, in the end the gain that we get from these more complex models is just marginal. It's a minor gain relative to this simple approach where we assume that the curve changes in a parallel fashion. And why is that? Because I mean, as you have seen in that animation in the first video of this chapter, when you look at how the yield curve moves, it moves mostly in a parallel way. Okay, and you can actually do a statistical analysis of those movements, and it has been shown many times in many markets that parallel changes are I forget the number exactly, but more than 90% of the variation in rates. So it's simple and it works relatively well, even though it's not the end of the story. It's not everything that we can do. Can improve a little bit with these models, but not that much. All right, and that's it.